Lab 2, Magnetic Field of a Bar Magnet by Dhilan Nanji. In this video, there will be an introduction, we'll discuss the computational model, there will be a discussion of the results, and then conclusions with the what-if questions. Introduction. Purpose. The purpose of this experiment was to determine the effect of distance on the magnetic field of a bar magnet and compare the measured values of this quantity to theoretical calculated values using the Biot-Savart law. The experiment. To determine the magnetic field created by a bar magnet, a magnetometer smartphone app was used. The system of interest is the magnet and the magnetometer. To account for the Earth's magnetic field, the smartphone was aligned to the magnetic north, where the x-component is zeroed, and the effect on the x-component, now unaffected by the Earth's magnetic field, was used to determine the field strength at varying distances on the axis of the magnet. The main results: the magnitude of the x-component of the magnetic field of the bar magnet increased as the distance decreased. See discussion for a more detailed depiction. For the off-axis position, the net magnetic field is 1.83 times 10 to the negative fifth Tesla. The value of n found was negative 4.91. The magnetic dipole was 0.20028 amperes times meters squared. The main key concept for this lab is the Biot-Savart law, which deals with the magnetic field created by moving charges. The two above equations are derived from the Biot-Savart law, and the second equation shows the field at off-axis points, which will be shown later in the computational model. And the upper equation is the dependence of the magnetic field on distance. This is the computational model for this experiment. The following equation used to calculate the electric field at the 7 points shown by each arrow. This equation was translated into this function below to calculate the magnetic field. The teal arrows are perpendicular to the axis of the magnet, and the orange arrows are on the same axis. The magenta arrow is at the 45-degree angle. Discussion. Initial observations. When the magnetometer is far from the magnet, it measures a near-zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. This is consistent with the previously shown equation where the magnitude of the magnetic field is proportional to r to the negative third. This is the data for the on-axis points. The strength of the x component of the magnetic field is indirectly proportional to the distance between the magnet and the observation location as shown by the table on the right, where there were multiple measurements taken at varying distances, and the graph on the left with a negative slope, which plots the natural log of the x component versus the natural log of r, x component of the magnetic field. But we can use this best fit line and match it up with our equation below to find that the natural log of k is equal to negative 17.003 or 033 and n equals negative 4.91. Using the value for the natural log of k and the steps below, we can calculate the value of the magnetic dipole moment. By rearranging and solving for mu, we get a magnetic dipole moment of 0.20028 amperes times meters squared. This is the data for the magnetic field at the 45-degree angle point. The measured distance, where the field is 100 microtesla in the x direction, was 0.225 meters. The distance from both x and y components was 0.319 meters. The bottom row shows the averages for each column. The magnitude of the net magnetic field was 1.83 times 10 to the negative fifth Tesla. Comparisons. The magnitude of the net magnetic field found by the model was 9.83 times 10 to the negative 7th Tesla, while the experimental data gave a value of 1.83 times 10 to the negative 5th Tesla. The model predicted a much smaller magnetic field. This may be due to using a calculated value for the magnetic dipole in the program that could be incorrect, or the experiment could have had significant error. In addition, the experimentally determined value for n was negative 4.91 as opposed to the theoretical value of negative 3. For the assumptions, the model assumes that there are no outside influences on the magnetic field, such as the Earth's magnetic field, nearby electronic devices, and metal objects. For the sources of error, the rulers and meter sticks used to measure the distance between the magnetometer sensor and the magnet may have moved during measurement. Alternatively, the phone may have rotated slightly. The experiment was done inside, as it could not be conducted outside due to weather. While there are no electronic devices nearby and limited metal, the carpet flooring was not perfectly even when moving the phone. The conclusions and the what-if questions. In the experiment, you orientate your setup so as to compensate for magnetic north. What if you hadn't done that and instead laid out your meter stick at an intermediate angle with respect to Earth's magnetic field? How would your results have changed? If the setup had not been oriented to account for magnetic north, there would be a non-zero x component prior to introducing the magnet to the system, and the x component would have to be corrected in a similar manner to the y component in the 45-degree angle experiment. In addition, the y component would have to be measured at each distance, as it would change more significantly by increasing proximity to the magnet, as it would not be directly perpendicular. What if, imagine you had two identical magnets? What if you redid the experiment, but instead of using a single magnet, used two identical magnets stuck together end to end? How would you expect your measurements to differ? The field strength would increase, the magnets combined would produce a field almost twice as strong as the original, but since one magnet is slightly further away from the magnetometer, it would have reduced field strength.